Okay, so the question is which combination will produce an alkaline buffer in water? So we know that alkaline buffer is produced by mixing weak base and its salt with strong acid. So the four options are given to us. We see that in option B there is a weak acid and strong base. So this cannot make an alkaline buffer. So this is not an option. In option C, we see that this is a combination of weak acid and strong base. So this will also not give us alkaline buffer. So definitely C and B are not the option. Now the left options are option A and option B. In option A, we see that ammonia is reacting with HBr and this will give us ammonium bromide. So we see that 0.05 mole of ammonia is there and 0.1 mole of HBr is there. And since ammonia and HBr is 1:1 reaction, 1 mole of ammonia reacts with 1 mole of HBr. So 0.05 moles of ammonia, 0.05 moles of ammonia will react with 0.05 moles of HBr to give us 0.05 moles of ammonium bromide. So at the end of the day, from option A we will get 0.05 moles of ammonium bromide and left over 0.05 moles of HBr. So this don't form a buffer. So the only option left is option D. So the correct answer is option D. So let us check option D. In option D we have ammonia 0.1 mole and nitric acid 0.05 moles. So reaction of ammonia with nitric acid will give us ammonium nitrate. So 1 mole of ammonia reacts with 1 mole of nitric acid to give 1 mole of ammonium nitrate. So therefore 0.05 moles of ammonia will react with 0.05 moles of nitric acid to give 0.05 moles of ammonium nitrate. So ammonium nitrate will be 0.05 moles and the leftover 0.05 moles of ammonia. So this will be our buffer, which will be a basic buffer, alkaline buffer. So the correct option is option D. Okay, so the question is a buffer solution is formed by mixing equal volumes of 1.00 mole per dm cube propionic acid and 0.500 mole per dm cube potassium propanate. What is the concentration in mole per dm cube of H plus ion in this buffer solution? K of propionic acid is given. So we know from the buffer Henderson-Hasselbalch equation pH of the buffer equals to pKa plus log concentration of A negative, that is the conjugate base, divided by concentration of acid, weak acid. So this equation we know. pK is given to us and concentration of conjugate base will be the concentration of potassium propanate and the concentration of weak acid will be the concentration of propionic acid. So we just plug in the values. pH equals to pKa. How can we calculate pKa from the Ka value? So from the Ka value, pK will be minus log to the base 10 of Ka. Ka is given. So this plus log concentration of conjugate base will be 0.500 divided by concentration 1.00. So this value is, we take the log of this and it comes out to be 4.886 plus then the log of 0.5. So this is minus 0.301. So 4.886 minus 0.301 comes out to be 4.585. So this is the pH of the buffer. In order to calculate the H plus ion concentration, we know H plus ion concentration is 10 to the power minus pH. So our pH is this, and when we solve this, this will come out to be 10 to the power minus 4.585, that is 2.60 into 10 to the power minus 5. So this is the answer. So option A is the correct answer. Okay, so the question is, which of the following mixtures would result in the pK of the acid being obtained from direct pH measurement of the resulting solution? So in order to calculate the pK of the acid from direct pH measurement, we should have a buffer, right? We should have an acidic buffer. So if we look at the option A, in option A we have HCl and we have NaCl. So there is no reaction between strong acid and salt. So it is not a buffer. So option A is wrong. Then in option B we have strong base, sodium hydroxide, and weak acid, acetic acid. The volume and concentration of both are same. So this strong base will completely neutralize the weak acid, and we will only have sodium acetate in and the water left. So this is also not a buffer. So this is also not an option. In option C, we see that acetic acid and sodium hydroxide are there, and the concentrations are same, the volumes are different. So we see that sodium hydroxide is in excess and acetic acid is limiting. So when they react, we will have sodium acetate in the solution and we will have sodium hydroxide. So this is also not a buffer. So we are only left with option D. Let's check the option D. In option D, we have sodium hydroxide is limited and acetic acid is in excess. So this will react to give us sodium acetate, and the leftover acetic acid will be there. So yes, this is a buffer and it will give us acidic buffer. And from the titration curve we can directly obtain the pK of the acid. So the correct option is option D. Okay, so the question is, which combination of acid and base is most likely to have a pH of 8.5 at the equivalence point in a titration? So which titration will give us the equivalence point greater than 7? When we have a titration of weak acid with a strong base. So the titration of weak acid, when weak acid is an analyte and our titrant is a strong base, in that case we will have an equivalence point at pH greater than 7. So in these options I can see that only option D, we have a weak acid and it is getting titrated with sodium hydroxide. So we will have a titration curve. So pH over here, pH 14, 0 to 7, and this is the volume of titrant, and our curve will be like this. So the equivalence point will be greater than 7. So the correct option is option D. So the question is, which titration curve would occur when a weak acid is added to a strong base? So it means that strong base is our analyte and weak acid is the titrant. So we will take weak acid in the burette and strong base in the conical flask. So our pH will start from because we have a strong base, so our pH will start from close to 14. So close to 14, so I can see option B, and then uh, the end will be at pH close to 6 or 5 or something like that of a weak acid. So the correct option is option B. Option B. Because if we look at option C, we see that the end of the titration is at very low pH, which is not possible because our titrant is a weak acid. So it should not end at pH very close to 1 or 0. So C is not an option. A is also not an option because we have our analyte as a strong base. So the pH will be constant, close to 14. It will not drop sharply, and also at the end this pH will not be so close to 0 and 1. So this is also not an option. Option D, it is not a titration curve at all. It looks something very strange. So only option B is the option. Okay, so the question is the acid base indicator phenol red HIN changes color from yellow to red over a pH range of 6.6 to 8.2. Which statement is correct? So we know that HIN is our indicator, which is a weak acid. It dissociate into H plus ion and partially dissociate into this, right? So HIN has yellow color and IN has red color. So option A says that in a strongly acidic solution. So strongly acidic solution means when we have more concentration of H plus ion. So if we have more concentration of H plus ion, this equilibrium will shift towards left. So we will have more of HIN concentration compared to ion negative in strongly acidic solution, and the color will be yellow because we will have more concentration of undissociated acid. So option A is not correct. Second option, the pK of phenol red is between 6.6 and 8.2. Yes, this is the correct answer. This is the correct answer. How about option C, the ion negative ions are yellow? No, that's not. Ion negative ions are red. Phenol red would be suitable indicator for titration of a strong acid and weak base. The equivalence point for strong acid and weak base is lying towards less than 7, right? At less than 7. So this cannot be used because the pK of this is between 6.6 to 8.2. So the correct option is option B. Okay, so the question is which indicator would be the most appropriate for titrating aqueous ethylamine with nitric acid? We know that ethylamine is a weak base, CH3, CH2 and H2, because it is an organic base. It's a weak base. And nitric acid is an inorganic acid. So this is a strong acid. So the equivalence point of this titration will be at pH less than 7. So if this is the titration curve, pH on the y-axis and volume of titrant on the x-axis, and suppose this is 14, this is 7 and 0. So this will start from here, go like this and like this. So the equivalence point will be here somewhere. Okay, so this is at pH less than 7. So we should choose an indicator whose pKa value lie between this and this. Okay, so in option A, phenol red, pKb is given. So pKa will be 14 minus 8. So this will be 6.0. So this is very close to 7. which is coming at the just at the edge of where our this drop in pH occurs. So this cannot be an appropriate indicator. Option B, we see the pKa is 7.3, which is more than 7, so obviously this cannot be used. Okay, then option C, pKa is 4.1, so it will be somewhere here. So yes, this can be an appropriate indicator, option C. And option D, pKb is given, so pKa will be, for option D, pKa will be 14 minus 4 is 10. So this is going beyond this somewhere here. So this is not an appropriate indicator. So option C is the appropriate indicator. So the question is, for which titration can the endpoint not be determined accurately by using an acid-base indicator? So we know that for weak acid and weak base titration, the endpoint cannot be determined accurately by indicator. So which is a combination of weak acid and weak base? We see that in option A we have weak base and weak acid. So yes, this is the correct answer. If we look at option B, we have a strong base and strong acid, so this is not. And in option C we have weak base and strong acid, so this is also not an option. And option D, we see we have a strong base and weak acid, this is also not an option. So the correct option is option. Okay, so the question is, an acid base indicator HIN dissociate according to the following equation. Which statement about this indicator is correct? In a strongly acidic solution, color B would be seen. So if there is a strongly acidic solution, it means we have high concentration of H plus ion. So when we have high concentration of H plus ion, this equilibrium will shift towards left. So we will see color A. So option 1 is wrong. In a neutral solution, the concentration of H ion and I negative must be equal. No, it depends on Ka. So they may or may not be equal. So it's not the correct answer. It is suitable for use in titration involving weak acid and weak base. No, for weak acid and weak base, indicators may not be used to find the correct endpoint. So all the three options are wrong. So option D. Okay, so the question is, which curve is produced by the titration of 0.1 mole per dm cube weak base with 0.1 mole per dm cube strong acid? So our analyte is a weak base and our titrant is a strong acid. So the titration curve will start from pH greater than 7. So option A is not the correct option, and option D is also not a correct option, because here the pH titration curve is starting from pH less than 7. So either option B or option C. So since our analyte is a weak base and it is getting titrated with strong acid, so the correct option is option C. So the shape of the curve will be like this.